Hello everyone, and this is Matematic. In this lesson I will talk to you about infinitely decreasing geometric progression. First, let's talk about what is a geometric progression. Basically, geometric progression is a sequence of numbers. The sequence can be written as b1, b2, b3, and so on. Bn will represent the upcoming numbers in the sequence. The first number in the geometric progression, or b1, cannot equal to 0. Also, I want to clarify that n in the Bn stands for a natural number. To find the next number in the sequence, which is Bn plus 1, we can multiply the previous number by the rate of change in the sequence. The previous number in this formula is Bn, and the rate of change is q. To make the equation more clear, let's assume that n equals 3, so the fourth term in the sequence will be equal to b3 times the rate of change q. Now let's look at some real examples of geometric sequences. Alright, so here's our first sequence. 1, 3, 9, 27, and so on. The rule for this sequence is 3 to the power of n minus 1. By looking at this sequence, we can conclude that b1 is 1, and the rate of change q is 3. Let's look at another example. Here we have a sequence 1, 1 over 5, 1 over 25, and so on. The rule for this sequence is 1 over 5 to the power of n minus 1. By looking at the sequence, we can conclude that b1 is 1 and q is 1 over 5. To find the nth term of the geometric sequence, we can use the formula Bn equals b1 times q to the power of n minus 1. We can use this formula if the term before the nth term is unknown. Now let's talk about how can we find the sum of the first n terms in the sequence. The formula for the sum is b1 multiplied by the difference of 1 minus q to the power of n, and divide the product of those by the difference of 1 minus q. So we use this formula whenever q doesn't equal to 1. Now you're probably wondering, how do we find the sum when q equals to 1? Don't worry comrades, there is a formula for this case. The formula we're going to use to get the sum is s equals to b1 multiplied by n, where the first term is multiplied by n, and n stands for the location of the number in the sequence. Now let's talk about infinitely decreasing geometric progressions. So here we have a few squares. The side of the first square is 1, side of the second square is 1 over 2, and side of the third square is 1 over 4, and so on. If you notice, there's a geometric progression going on. By looking at the picture, we can conclude that b1 equals to 1, b2 equals to 1 over 2, and b3 equals to 1 over 4. The rate of change of this progression is 1 over 2. Now we can write the side progression in the proper format. The side progression will be 1 followed by 1 over 2 followed by 1 over 4 and so on. And the rule for this progression is 1 over 2 to the power of n minus 1. The example of the squares was an infinitely decreasing geometric progression. The example had shown us the key characteristics of infinitely decreasing geometric progressions, which are As n increases, the value of the nth term becomes more closer to 0. And another characteristic is that the absolute value of the rate of change has to be less than 1. Now let's look at another example. In this example, the squares are constantly being divided into halves. All of you will agree that if we add all of the areas of these squares together, the total sum will equal to 1. By looking at the picture, we can conclude that with every new division of a single square into halves, the area of a single square will be more closer to 0. Now let's find the formula for the sum of the n terms. So here we multiply 1 over 2, which is b1, by the difference of 1 minus q to the power of n, and in our case q is 1 over 2. Then we divide by the difference of 1 and q. And the formula for the sum of n terms will be 1 minus 1 over 2 to the power of n. Based on our observations, we can conclude that 1 minus 1 over 2 to the power of n will approach 1 with every single square division. Now let's look at another example. Here we have a sequence. 1 which is followed by negative 1 over 3, followed by 1 over 9, and followed by negative 1 over 27, and so on. The rule for this sequence is negative 1 over 3 to the power of n minus 1. By looking at the sequence, we can conclude that b1 equals to 1, and the rate of change in this sequence is negative 1 over 3. By looking at the rate of change, we can conclude that this is an infinitely decreasing geometric sequence. The sum of the first n term is 1, the sum of the first two terms is 2 over 3, and the sum of the first three terms is 7 over 9. Now let's find the formula for the sum of n terms. So our formula will be 3 over 4 minus the product of 3 over 4 and negative 1 over 3 to the power of n. Now we can conclude that as the sequence goes on, the term's value will start to approach 0. And the sum of the sequence will approach 3 over 4. The formula for finding the sum of infinite geometric progression is S equals B1 over 1 minus Q. Now let's do some practice problem. In this problem, we have to prove that Bn equals to 3 over 5 to the power of n is an infinitely decreasing geometric progression. First of all, we have to find the first few terms in the sequence. The first term in the sequence will equal to 3 over 5, and the second term will equal to 3 over 25. Now we can calculate the rate of change. We can calculate it by dividing b2 over b1. and the rate of change will equal to 1 over 5. Our rate of change is less than 1, which makes the sequence an infinitely decreasing geometric sequence. In this problem, we have to find the sum of the sequence. So the rate of change of the sequence is negative 1 over 3. Our sum formula is b1 over 1 minus q, and when we plug in the numbers, it will be 1 over 2 divided by 1 minus negative 1 over 3, and our answer will be 3 over 8. If you enjoyed this video and found it helpful, please like and subscribe to my channel.